In this video, we'll be looking at the first part of the further mechanics booklet, circular motion. Now, when dealing with motion in a circle, it is important that you set your calculators to work in radians. So instead of using normal measurements for angles in degrees, we must instead use the radians setting, which puts things in an equivalent value of pi. So, for example, in this case, pi is the equivalent of 180 degrees, whereas 2 pi will be 360 degrees, full circle. So it's obviously possible to convert between the two by dividing by one and multiplying by the other, but turning a calculator into this setting is necessary for some of the calculations to work. So when we're dealing with angular speed, it clearly must be different to our previously considered speed measurements or velocity measurements. So instead of having linear speed, which would be the speed along a tangent or a velocity at any point in the rotation, we must deal with something different. So the angular speed will be about the rotation around the circle per second, so radians per second instead of meters per second. So it's how much of the circle is actually covered in that time. Now, for this you are given equations, and we're introduced to this symbol here, this W symbol. That is lowercase omega, and that represents our angular speed, which, as we've said, is measured in radians per second, or rad s to the minus 1. V is our linear or tangential speed. So standard velocity really as far as we consider it. And that is still measured in meters per second. And then we have R for the radius. And radius is the radius of the circle that you're actually moving around, and it is measured in meters. This luckily ties everything together nicely, because meters per second divided by meters gives us per second, and as we're dealing with angle of rotation, radians is put into that as our unit. So this allows for straightforward conversion. We also have to relate to frequency. So whenever you're dealing with rotations, so circular motion, you're dealing with repeated cycles, continuous motion around and around. So as a result, frequency has quite significant meaning. So our number of revolutions per second for the frequency can also be converted into time period, which is not given. So the equation here that is given is that our angular speed, omega, is 2 pi f. So again, omega is our angular speed in radians per second. 2 pi is obviously just a number, and f is our frequency measured in hertz. Now it's worth remembering that hertz is just the same as per second, again showing that the unit works, as we are just talking about rotations in radians. Now, you know that frequency and time period are related by this inverse function, f equals 1 over t. Therefore, we can easily translate this equation to be omega equals 2 pi over the time period. So whilst you're given that relationship between frequency and time period in the waves topic, you're not shown omega equals 2 pi over t in the circular motion section. It's assumed to do that yourselves. Now, force and acceleration are both important features of any rotating system. So we can see that if we have our velocity moving tangentially from this object, if that object continues in its circular motion around the central point, it will be changing direction. And it's constantly changing direction. As a result, it is being accelerated, because that's what our definition of acceleration is. An acceleration, as we all know, due to F equals ma, must be caused by a resultant force. So this is where we have a centripetal force, a force acting towards the center of the circle. And the acceleration acts along exactly the same line. So it's very easy to recognize where these are. So we have a centripetal force and a centripetal acceleration, both center pointed. So, as far as equations go, you do get some formulae for these. Now, to start off with, we have to consider the acceleration, because that's the easiest one to first acknowledge. And that is given to us in two forms, where the acceleration is equal to v squared over r, and it's also omega squared r. Now, we know that omega is our angular speed, given in radians per second. We also know that r is the radius of the circle itself, which now has meaning, obviously, based on the direction of the acceleration and force. And v is our linear speed, or the velocity as it's shown in the diagram above, in meters per second. So our acceleration retains its standard unit, meters per second squared. Nothing fancy or special happening there at all. And you can see that these equations allow a bit of play to manipulate and determine v or omega from the acceleration itself. Now, for force, it's actually a very simple recognition of the fact that F equals ma, as we've already said. So if that's the case, all we're doing is multiplying through the above equation on acceleration by m. So F equals mv squared over r, and it also equals m omega squared over multiplied by r. So the only additional thing here is that m is mass in kilograms, and F is our force in newtons. Very straightforward equations, all given to you, apart from the relationship between frequency and time period. All you have to do is apply them. Thank you for your time.